Hello students, this is the Chapter 8 presentation on sampling distributions. Remember during the last chapter, during Chapter 7, we talked about the normal distribution. Here we're going to be applying that to not just looking at individual samples, but looking at multiple samples. And you'll see that even looking at samples rather than individual observations, that will still follow that sampling distribution, that normal distribution. And the definition here is the sampling distribution is the distribution of a statistic across an infinite number of samples. Hopefully I will be able to explain that using a couple of examples. Here are the objectives for this section. I'm going to be describing the distribution of the sample mean from a normal population and describing the distribution of the sample mean from a non-normal population. Remember, we talked about populations that might be skewed or might have a uniform distribution or might have a bimodal distribution. So we're going to be able to describe both of these distributions. Spoiler alert, they're going to be very similar. This is an example about comparing the mean for the population and the mean of the sample for the players for the 2008 men's Olympic basketball gold medal game. You should recognize some of these names. They're legends in the game. Jason Kidd, LeBron James, Kobe Bryant, Carmelo Anthony, and Dwight Howard. And you can see their heights are listed here in inches. We found the mean and we found the standard deviation of this population, of these 5 basketball players. And one thing that you should recognize is all 5 of these players added together and divided by 5 is 79 inches. If you were to sample from this population, but you were only to sample, let's say for argument's sake, 2 of the basketball players, do you think that the mean would be higher or lower than 79 inches? Well, the answer is sometimes it would be higher and sometimes it would be lower, depending on which 2 people that you select. For example, if you select Jason Kidd and Kobe Bryant and find the average between those 2 measurements, that would be smaller than 79 inches. On the other hand, if you were to select LeBron James and Dwight Howard and try to find the average of their 2 heights, that would have a mean that is higher than that population mean. Here's a chart that summarizes what I'm talking about here. If we were considering the samples of size 2, in other words, if we were considering taking 2 of these players and finding the average height, and remember that X bar stands for the average of a sample. For example, between Kidd and James, the average would be 78. Between Anthony and Howard, the average would be 80.5. But I want you to notice something. All of these are the sample means, the averages of the samples. And all of these numbers are actually pretty close to 79, which was the population mean. And that should make sense to you because they're sampled from the same population. So if you're sampling from the same population, sometimes the sample mean will be lower than the population mean. Sometimes the sample mean would be higher than the population mean. But all of them are pretty close to the population mean. There's, oh wow, what just happened there? There is a chart that summarizes that same thing. Here's the graph. If you were looking at all the means for different sample sizes, if you look at this graph, for example, this is all of the samples of size 1. And you should say to yourself, well, there's 1, 2, 3, 4, 5 dots. Why are there only 5 dots? Well, remember, there are only 5 players in the whole thing. So if I'm taking samples of size n equals 1, I'm basically saying I'm going to sample 1 player. Sample 1 player, sample 1 player, 1 player, 1 player. So that is why this graph has only 5 dots, because this dot represents Jason Kidd, for example. This dot represents Dwight Howard and everyone in between. This is the samples of size 2. So this is when I take 2 basketball players and I add their 2 heights together and divide by 2. Notice that all of these numbers, some of them are below and some of them are above 79, but they're kind of grouped around the mean, the population mean. If I took samples of size n equals 3, in other words, if I said, all right, I'm going to pick 3 of these basketball players and I'm going to add their heights together and divide by 3, you can see that the results, the sample means, are even closer to the population mean. If I were taking samples of size n equals 4, they're even closer to this population mean. And if I were taking samples of n equals 5, which means I'm essentially taking the entire population in this case, then the sample mean is exactly equal to the population mean. This is the concept that I'm trying to get across to you. If you're sampling from a population, the larger the number of items in your sample, in other words, the larger your sample size, the closer your sample means are going to get to the population mean. That is a very fundamental piece of information or concept for this lesson. Now there's another way to interpret what I just said. Here's the other way to interpret what I just said. As the number of items in the sample, as the sample size increases, the spread of these samples decreases. In other words, the standard deviation of the sample means is decreasing. So if I make n go higher, my standard deviation goes lower. That's a concept that we're going to see in a formula fairly quickly. You should remember from the previous lessons that the term random variable talks about the value varying from sample to sample. Statistics like x bar, or the sample mean, are random variables because their value varies. So they have probability distributions associated with them. So if you're looking back at one of these distributions, the probability that you get mu, the sample mean, it's higher in the middle, and the probability that you get a smaller mean than that or a larger mean than that is lower. So that's what we talk about when we talk about a probability distribution. Here we're going to be talking about the shape, the center, and the spread of these statistics. We already talked about the spread, and we already talked about the center. When I'm looking at these these probability distributions, the center of all these distributions is the population mean. That's important. And also, as the n increases, the sample size increases, the spread, or the standard deviation, is going to decrease. Very important information here. Remember that sampling distribution from the top of the video. It is a probability distribution for all possible values of that statistic computed from a sample size of n. So every time that you pick a sample, you're going to pick the same number. Remember the example from before, we're always going to pick 2 basketball players, for example, from the population, and we're comparing all of those samples of size n. The sampling distribution of the sample mean just says we're going to take a sample, and we're going to find its sample mean, and we're going to plot it. We're going to take another sample, find its sample mean, and plot it. We're going to do that over and over and over again until we get enough or a large amount of sample means. The sampling distribution of the sample mean ideally is all of the samples, all possible values of the random variable x bar, which means all possible samples of size n. The example that I showed you before, this example, is a sampling distribution of size n equals 2 because there are only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different possible values of x bar when I'm picking from these basketball players because there's 5 options and 5 choose 2 is 10. All right, where are we at here? We just did this, we just did this. Let's start talking about what a sampling distribution is. The first step in looking at a sampling distribution is obtaining a simple random sample of size n, kind of like choosing 2 basketball players from 5. The next step is to compute its sample mean. So I pick a sample and I compute its sample mean. The third step is to repeat steps 1 and 2 until all simple random samples of size n have been obtained. Now, in general, when we're doing this in statistics or when we're doing it in any other sort of field, we're not going to be able to pick all random samples of size n. So what we try to do is we try to pick as many as possible, and once we pick something that we refer to as enough, we'll see that the sampling distribution is illustrated there. All right. Now, what if the population that we're picking from is normal? In other words, what if that population has a normal distribution in terms of its values? Let's say that some values are very small, some values are very big, but most values are here at the peak, which we call the mean. And please ignore my crooked line here. It's difficult to draw on a computer. In most situations, our population is quite large, so we can't look at every possible sample mean. I just talked about this because instead of looking at a population of only 5 basketball players, sometimes we're looking at the population of all the pennies in the world, or we're looking at all the adults between 18 and 34 in the United States. Most of the time, our population is impossibly large, so we couldn't possibly pick every sample mean. However, we can simulate sampling by using a computer program, or we could pick until we have enough to define our sampling distribution. Here's an example. The weights of all pennies minted after 1982 are approximately normally distributed, with mean 2.46 grams and standard deviation 0.02 grams. Now, before we even talk about anything else, you should be able to draw the distribution of this population. Remember, the distribution of this population is normal. So we can draw that normal curve. And we could say this middle here, the center, is the mean. So that would be 2.46 grams. And you should also be able to observe that we have the mean, which is 2.46 grams. We also have the standard deviation, which is 0.02 grams. So we would be able to draw the inflection point below and above. And we'd also be able to draw the other standard deviations below and above. All right, I'm no artist, but this is a pretty good rendition. Now, we're supposed to approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n equals 5. In other words, here's what we're doing. We're going out into the world and we're finding 5 pennies that are minted after 1982, that are created after 1982. And we're going to weigh all of those 5 pennies and then add those numbers together and divide by 5. That is finding one sample mean. So once we find one sample mean from a sample of size n equals 5, we're going to go out and do that, that's right, 200 times. So 200 simple random samples, 200 samples of 5 pennies, and we're finding the sample mean. In other words, we're weighing them all and adding those together and dividing by 5. So remember, this right here is an example of the population distribution. So this is the population distribution. So the question is, if we were to take 200 samples of 5 pennies each and weigh those pennies, what do you think would happen? What do you think the sample means would look like? Well, it should make sense to you that if the entire population has a mean of 2.46 grams, sometimes when we sample 5 pennies, some of those samples are going to have a weight that is higher than 2.46. Sometimes we'll get a bunch of really heavy pennies, and sometimes, they'll be over here. Maybe we'll get a heavy sample, or maybe we'll get a sample that's over here. And sometimes we'll get a sample of pennies in which, maybe the pennies are older and they've been eroded away. Maybe people have been, clinking them in their pockets often. So that means that they've lost a little bit of their mass. Sometimes we'll have, lighter pennies over here or over here. But I would say that most of the time, if this is really the mean of the population, most of the time we take a sample of 5 pennies and we find the average weight. Most of the time it's probably going to be pretty close to 2.46. That's what we expect to find. So here's an example of what could happen. The first sample of n equals 5 had the following data. These are all of the different pennies that are in our first sample. We went out and found 5 pennies that fit that criteria. And we found that their weights are all sort of near the 2.479 figure. Notice that this one is above, this one is below, this one is almost exactly accurate, and so is this, and this one is a little bit above as well. If we were to do that over and over and over again, if we were to do sample means for samples of size n equals 5, I believe this is 200 examples. This is then one example of a sample mean. This represents, I went out and found 5 pennies, I weighed them all, and I added those weights together and divided by 5. Same thing here. I found 5 pennies, I added their weights together and divided by 5. I found 5 pennies here, I added their weights together and divided by 5. These are all sample means. Keep in mind, this is something that students sometimes confuse. This is not individual pennies. This does not represent one penny. This represents the weights of 5 pennies averaged out. This is the weights of 5 pennies averaged out. Okay, great. Hopefully you understand that piece. Now the mean of the 200 sample means, in other words, we took all of these values and we added them up and we divided by 200 because these are all sample means. And we say, okay, now let's find the average of the sample means, or the mean of the sample means. The mean of those 200 sample means is 2.46, which is the same thing as the mean of the population. And notice that it says the same as the mean of the population, but in point of fact, you should remember that the mean of that population is 2.479. So this mean of the sample means is extraordinarily close to the actual real population mean. It's not exactly the same, but it's very, very close. And that's what we expect. After we take the 200 sample means, we find all of their individual means, and we find the mean of those means. 2.46 is very close to 2.479. And the standard deviation of the sample means is 0.0086. Wow, this is a very small number. That means that the standard deviation of the sample means from the actual mean is very, very small. It means that they're all very close to that sample mean. The next slide is going to show the histogram of the sample means, and you can see in this histogram the center is right about here, 2.46, And you can see that there are some that are smaller, some that are larger, but there's a very significant drop off here. It's very, very unlikely to get one of those 200 sample means that is lower than 2.435. And it's very, very unlikely to get a sample mean from one of those 200 samples that is higher than 2.48. Notice that the cluster or the grouping here is very, very close to the mean. That's why we say the standard deviation is very low, 0.0086. All right. Remember, as the size of the sample gets larger, remember back to the basketball example, we do not expect as much spread since larger observations will offset smaller observations. So if I were to pick two basketball players and I happen to get a shorter person, like a Jason Kidd, that short person, would be a small observation. That means that the mean would get thrown off by that observation. However, when I take a larger sample, if I were to sample 3 or 4 basketball players rather than just 2, a smaller observation would be offset by another similarly larger observation. So the mean would get closer and closer to the actual real mean. This is known as the law of large numbers. The law of large numbers can be summarized by this. As n increases, as the size of the sample increases, the difference between the sample mean, I need you to be able to read this as sample mean, and the population mean approaches 0. In other words, the sample mean value is going to get closer and closer to the population mean value. All right. So what would happen if we were to do the same exact procedure? However, instead of picking out 5 pennies in every sample, you could probably find it here, we're picking out samples of size n equals 20. In other words, instead of picking 5 pennies, weighing them all, adding them together, and dividing by 5, we're going to pick 20 pennies, add them all together, divide by 20 to find the sample mean of that sample of 20. What do you think would happen? Well, the answer is that we would get the same exact mean, 2.46. Amazing. However, the standard deviation is now 0.0045. That is much smaller than the standard deviation when I picked out samples of n equals 5. So the difference here is that the mean of the sampling distribution is still 2.46. But the standard deviation is much lower. You can see that you should remember that the tails went out all the way, I believe, to 2.43 or 2.41. This tail isn't going quite as low. And same thing here, this tail isn't going quite as high as 2.483, which I believe is the other one. This one only goes out to 2.475. So the sampling distribution using n equals 20 is going to have the same center, but a much smaller spread. Less variability, smaller spread, smaller standard deviation. Fantastic. All right. Now, if you were to do this, rather than doing an experiment, if you were to try to figure out the standard deviation of a sampling distribution mathematically, there's an easy formula for it. Suppose we're trying to pick a simple random sample of any size, doesn't matter what the size is, from the large population with this mean, the population mean, and this population standard deviation. The standard deviation of the samples, the way that we read this is the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of n. Why do we square root n? Good question. Statistics. The standard deviation of the sampling distribution of x bar of the sample mean is called the standard error of the mean. So this right here has 2 different meanings, and I'm going to write the 2 different meanings. Now you could call this the standard error of the mean, or you could call this the standard deviation of the sampling distribution of the sample mean, which is longer to say. That's why statisticians prefer using just standard error of the mean. All right, moving on to the next section. Now let's talk about the shape of the sampling distribution of the sample mean. Remember that the shape of the population we talked about was normally distributed. I think we were talking about pennies before, right? So the shape of that population is normal. It should make sense to you that the distribution of the sample mean x bar is also normal. Makes sense. A normal distribution is going to give you a normal distribution. When you sample from a normal distribution, you should also be getting a normal distribution from that. For example, IQ scores are, well, they're roughly normally distributed. We'll talk more about that later. With mean 100 and standard deviation 15, easy numbers to deal with. If we were taking a simple random sample of size n equals 20 from the population, it might be a little awkward because that means you're walking up to 20 different people and saying, hey, can I take your IQ? Can I give you an IQ test? Some people might be like, no, thank you. So if we were to do that, we were to take a random sample of size n equals 20, we're assuming they're willing volunteers, and trying to figure out what the mean and the standard deviation of that sample would be, it should be very, very straightforward to find the mean, because as we discussed previously, the sample mean should have the same exact average or the same exact center as the population. So we know that the population has mean 100. So the sampling distribution of the sample mean is also going to have a mean of 100. And keep in mind that this symbol is the mean of the sampling distribution, right? That subscript here and the X bar indicates it is the mean of the sampling distribution of the sample mean. All right, the standard deviation of the sample mean is, remember this symbol here, it's the standard deviation of the sample mean. There should be a little bar on top of here. I guess that didn't come through. Should be equal to the population standard deviation divided by the square root of n. Population standard deviation is 15. The n is square root of 20. This number is around 3.354. So I want you to observe something. The standard deviation here is 15 of the population. If I'm doing the sampling distribution of the sample mean, its standard deviation is going to be smaller, because as you pick more and more items in your sample, that will make your estimate of the mean more and more accurate. So here are two pictures. The first picture is in blue, and it says the standard deviation is equal to 15. That's this. That's, in other words, the population distribution. That's in blue. In red, you will see that the sampling distribution of the sample mean is a little bit different. In one way, it's the same though. The center of these two distributions is exactly the same. However, the spread of the population, how far the population is spread out, that's in blue here, is much larger. The spread of the sampling distribution is much smaller. The sampling distribution, we say, is less variable, because the sampling distribution has not samples of n equals 1, like the population. We're using samples of size n equals 20. All right. Now what we can do is, now that we have a normal distribution for the sampling distribution of the sample mean, we can use that to answer questions like this. What's the probability that in a simple random sample of 10 people, we obtain a sample mean of at least 105? Well, now we have a lot of information. Now we have the mean. Now we have the standard deviation. And remember that finding probability is the same as looking underneath a normal curve and trying to find the area underneath the normal curve from one part to the other. All right, just to make sure that you guys understand what's going on here, what I just did was I made a probability distribution. This distribution represents the sampling distribution of the sample mean, the sampling distribution of X bar. I found the mean very easily by saying, well, the mean of the the mean of the sampling distribution of the sample mean is equal to the population mean, which is equal to 100. And the standard deviation of the sampling distribution of the sample mean is equal to the population standard deviation divided by the square root of n. So 15 is the population standard deviation. I divided it by the square root of the sample size, which is 10. That's about 4.74. And I made the normal distribution based on that. I added 4.74 3 times, and I subtracted 4.74 3 times. You should be able to do this, for the test or for any other situation. Now the question is, what is the probability that in a simple random sample of size 10 people that we get a sample mean of at least 105? Remember, the sample mean is going to be represented in this distribution, and the sample mean is at least 105. So let's say 105 is here. At least means we're looking for values that are higher than 105. So this is the region that we're looking for when we're doing our calculation. Remember that this is a normal distribution, so we're going to be using normal CDF. Now think about the lower bound and the upper bound. The lower bound is going to be here. That's going to be exactly 105. Now, thinking about the upper bound is going to be up here somewhere. It doesn't just stop at 114.22, it keeps on going to positive infinity. But as I talked about in the previous video, we can't get to positive infinity on the calculator, so we're going to be using 10 to the 99th power. That's our upper bound. Now, if I'm talking about the mean and the standard deviation, be careful. The mean is 100, as it says in the problem. However, the standard deviation of the sampling distribution of the sample mean is not the same as the population standard deviation. We found this sampling distribution standard deviation, which is 4.74. So I'll show you what it looks like. All right, so you can see I put this normal CDF into my calculator. 105 is my lower bound, 10 to the 99th is my upper bound. The mean of the sampling distribution of the sample means is 100, and the standard deviation of the sampling distribution of the sample means, or in other words, the standard error, is 4.74. So I get 0.145746, etc. This is about a 14.57% chance that a child will have, that a sample mean will have at least 105. Now, sometimes the students ask me the question, what if I took this 4.74, which is the standard error, and I rounded it to something else? What if I rounded it to, let's say, 4 decimal places or 6 decimal places? Well, hopefully this illustrates the difference here. If I took that standard error and I rounded it not at all, if I put in all the numbers I found in my calculator, 4.74341649, etc., you can see that this percentage did not change a lot. 14.57% versus 14.59%. It is not a large change, and usually, we allow for differences in answers like that. So the answer to the question is, generally, it does not really matter where you round to as long as you round enough, and 2 decimal places in this case is enough because none of these other values is talking about decimals at all. So 2 decimal places is totally fine. 1 or 2 more decimal places than is in your data should be fine. All right. There are some questions on this presentation. I would like you to go through these questions and try to answer them on your own time. Very good. Now let's take a look at the same idea. The mean is 100 and the standard deviation is 15. Now, what if we changed the size of the random sample? What would happen then? It should make sense to you that the only thing that's going to change is not the mean of the sampling distribution, but the standard deviation will be different. Because our standard deviation of the population is 15. Now, instead of dividing it by the square root of 10, we're dividing it by the square root of, that's right, 20. That's a little bit different. I leave it to you to make that calculation yourself. In the second section here, we're going to be talking about the distribution of the sample mean from samples from a population that is not normal. So instead of using IQ scores, we might use weight or something like that. As you know, the weight of a population is going to have a right skew because it's very, very unlikely that a person will have a weight that's less than 0, but it is possible that a person has a weight that is many, many standard deviations above the mean. They could be overweight. All right, in this population, this should be familiar to you. This is a probability distribution. It lists out all the different faces on a fair die and the relative frequency. This is 1 divided by 6, 1 divided by 6, etc. These are the probabilities of landing on each of these faces. And you should recognize that this probability distribution is uniform. It's uniform because all of the different outcomes have the same probability. We are also able to calculate that the mean is 3.5. The mean should be the exact middle value of this distribution. So that's 3.5 right here. And the standard deviation is 1.708 based on a calculation that we were able to do. So now what we have to do is estimate the sampling distribution of the sample mean in this case by obtaining 200 simple random samples of size n equals 4 and calculating the sample mean for each of the 200 samples. So in other words, what we're doing is we are rolling 4 dice, the sample size of size n equals 4. We are adding all of those values together and dividing by 4 to find the sample mean, and we are doing that 200 times. So keep in mind, that's what these numbers indicate. So hopefully that makes sense to you. The n equals 4 means the 4 dice. The 200 means we're repeating the procedure 200 times. Now it then says repeat this procedure for n equals 10 and 30. The only thing that changes there is we're still doing it 200 times, but we're going to be doing it by rolling 10 dice and finding the average result, and then rolling 30 dice and finding the average result. This seems like a very arduous task, but luckily somebody's already done it for us. Let's take a look at the histogram of the sampling distribution. Here are the 3 histograms in question, and I want you to notice how they change over the different sampling methods. For example, this is n equals 4. This is what happens when we roll 4 dice. You can see that the mean is still about 3.5. You can see that the standard deviation or the spread of this this sampling distribution is pretty large. You can see that the 2 is out here, the 5 is out here. Looking here, we have the same mean, but the standard deviation or the variability is much, much smaller for n equals 10. And as we get to n equals 30, it kind of looks like a gradual tail off here, but keep in mind we're looking at the scaling. Look at the scaling here. The scaling from here was 3.5 down to about 1 and 3.5 up to about 6. This is only down to about 2.5, and this is only up to about 4.5. So you can see that the spread of this is much smaller than the spread of this and this. As the sample size gets larger, the spread gets smaller. And you should remember that that concept is called the law of large numbers. As the sample size increases, the difference between x bar and mu approaches 0, the spread becomes smaller. All right. Here's one thing that you already know. The mean of the sampling distribution is equal to the mean of the parent population. In other words, the mean of the sampling distribution equals the population mean. The standard deviation of the sampling distribution, we also know this as the standard error, is sigma divided by the square root of n. Remember, this is the standard deviation divided by the square root of the sample size, regardless of the sample size. So these are things that we knew from before. The central limit theorem says this. If you had noticed from previously, all of those sampling distributions came from a uniform distribution, but the sampling distributions were all normal. So the shape of the distribution of the sample mean is going to become approximately normal as the sample size n increases, regardless of the shape of the original population. So from a uniform distribution, if we take a sampling distribution, guess what? The sampling distributions are going to turn out to be normal. That should make sense to you because regardless of the shape of the population, every time that we take a sample, it's either going to be a little bit larger, a little bit smaller, or exactly the same as the population mean. That's very, very important information. That's called the central limit theorem. Doesn't matter what the population looks like. It doesn't matter where you come from. You're going to be normal. Inspirational, I know. There's one piece of caution here, though. It only has to do with the shape of the distribution of the sample mean. It only has to do with the fact that the sampling distribution is going to look like this. It doesn't necessarily talk about the center and the spread. Remember that the center is going to be mu, the population mean, and the standard deviation is going to be this calculation, which we've already gone over, regardless of the size of the sample. Keep that in mind. Here's an example that I'm going to provide an answer for, and I'll let you puzzle it through by yourselves. It gives us 11.4 minutes, which is the mean time for an oil change for all customers, and a standard deviation of 3.2 minutes. Keep in mind that these are population parameters. These are all values for the population. It asks for the sampling distribution of the sample mean, just a description. I'm going to draw it. And then it also asks, what's the probability that the mean oil change time is less than 11 minutes? I'm going to do it here now. All right, the first step says describe the sampling distribution. I've actually drawn the sampling distribution, but an easy way to describe the sampling distribution is as follows. The sampling distribution of the sample mean is going to have the mean of 11.4, and it's going to have a standard deviation, or standard error, I should say, of 0.541. And keep in mind, I had 1 decimal place here, so I took it to 3 decimal places. I think that it's only fair that you should take it to a couple more decimal places than the data that they give you. And then I actually drew the distribution here. Not necessary to do that, but if it did ask you to draw the distribution, here's what it would look like. Let's take a look at letter B. In letter B, it says if a random sample of n equals 35 oil changes is selected, same idea as what we did here, what is the probability that the mean oil change time is less than 11 minutes? So if it's less than 11 minutes, we're looking for less than 11. So on my diagram, it's good that I made this diagram here because here's 11. And less than would be shading downwards like this. So we're going to use that same concept of normal CDF, but we're going to be using our lower bound as negative infinity, or negative 10 to the 99th, and our upper bound as 11. So here's how that would look. Here's that normal CDF calculation. You got 0.2298. You can see it on the calculator here, 0.2298. And here are the answers to A and B formatted properly. And it is also on the slide for you to peruse. Again, here are a couple of questions here to try to identify whether you understand what you're talking about. Try these questions out, and if you are not sure how to do them, please contact me. For this one, suppose x is a random variable whose distribution is known to be skewed right. Oh no, skewed right, it's not normal. With this mean and this standard deviation, what's the probability of the sample, a random sample of size n equals 40, results in a sample mean that is less than 48? I'm going to write the answer down here. Hopefully you can try that out on your own. And here's our summary. We drew the normal distribution here. This is a sampling distribution, as we talked about previously. Here's our mean of the sampling distribution. We went up and down 3 times by this standard error, which is the standard deviation of the sampling distribution. Just the regular population standard deviation divided by the sample size's square root. We use normal CDF starting with negative 10 to the 99th, which is the negative infinity that we use in our calculator. 48 is the upper bound, 50 is the mean, and 1.58 is the standard error. We got 0.1028, 10.28% chance that a random sample will have a sample mean less than 48. Should be well understood by you by now. All right, moving on to section 8.2, which luckily is a little bit more straightforward and uses some of the same concepts. Now we're going to be talking about the sampling distribution of a sample proportion. I want you to think about the sampling distribution of a sample mean. Remember that all of the samples are from the same population, so all of the samples should have very similar values to the population mean. It's the same thing with proportions. If we take a sample proportion, that proportion should be very similar to the population proportion. So, another spoiler, the sampling distribution of a sample proportion is going to act very similarly. It's going to be a normal distribution, and it's going to be centered around the actual population proportion. All right, let's take a look at it. Suppose we're taking samples from a population in which each individual either does or does not have a certain characteristic. So what we use in statistics for the sample proportion, it's not P bar, kind of like X bar, the sample mean. It's called P hat, which is adorable because it has a little hat here, that caret. A P hat is given by X divided by N. X is the number of individuals in the sample with that characteristic, and N is the total number of individuals. Let's say we're looking for people with glasses, right? If we take maybe a class of size 34 students, and we see that 15 of those students have glasses, the P hat of all the people that wear glasses is going to be 15, the number of glasses wearers, divided by 34, which is the total number of people in that sample. Should be fairly straightforward. In 2008, Quinnipiac University put out a poll about whether they approved of George W. Bush. 349 people responded yes. So that means there's 349 people with the characteristic that we want, and there's 1,745 people in our sample. So this is the X, and this is the N. So a point estimate, remember point estimate is another way of saying a sample or a statistic for the proportion of registered voters. So what we're going to be doing is finding this point estimate, which is very, very straightforward. We're dividing X, which is this value, by N, which is this value. That should just be 0.2. That is our P hat. And remember, we're not using P, we're using P hat because this isn't every single registered voter in the entire world. This is just all the registered voters that were represented by the poll. All right. Same thing here. I'm sorry, this is a slightly different thing. We're now talking about the distribution of the sample proportion instead of just taking one sample. According to a Time poll in 2008, there are 42% of registered voters believing that gay and lesbian couples should be allowed to marry. It is much higher today, thankfully. Describing the sampling distribution with n equals 10, n equals 50, and n equals 100, it should be something that you could guess. As this sample size gets larger and larger and larger, you should be able to guess that 1, the sampling distribution of this proportion gets less and less spread, and 2, the sampling distribution is going to be closest, very, very close to that 42%. So it's going to have a small spread, and it's going to be normal. Here is the results of that situation. Lo and behold, look what happened. We said that 0.42 was the percentage for the proportion for the population. Now, when I used samples of n equals 10, the center is here, but it doesn't look that good. It doesn't look super normal. When I use samples of n equals 50, wow, look at that, 0.42. Here's my peak, and it tails off very, very precipitously. It's got a very small spread. 0.42 is my mean, and the spread is even better here. So as you could probably guess, as that sample size gets larger and larger and larger, the spread is going to get smaller and smaller and smaller. Remember, that's the law of large numbers. The shape should be very familiar to you. The shape is normal. the center of a sampling distribution of a sample proportion, you should know that the mean of the sample distribution of the sample proportion is equal to the population proportion. I'm going to use symbols to describe that here, and these symbols simply indicate the mean of the sampling distribution of the sample proportion is equal to the population proportion. And as we just talked about, the spread gets smaller as the sample size gets larger. For a simple random sample of size n, the mean of the sampling distribution of the sample proportion is equal to p, which is the population proportion, and this is a lot different than the previous example, but not super different. Keep in mind that the sampling distribution's standard deviation is going to be equal to something divided by n, and there's going to be a square root involved, similar to the standard deviation of the sampling distribution of the sample mean, or the standard error of the sample mean. The only difference is now we don't have population means, we have the population parameter for proportion. So we're using that instead of the mu, or the population mean. Before we are able to use this model, we have to check some certain conditions. Now, they're very, very stringent about these conditions on, let's say, for example, an AP test about statistics. But in this case, since we're just going to be dealing with situations where these conditions have already been verified, these aren't super important. But we are going to be assuming that they're finite populations. The populations are not infinite. And also that the sample size is no more than 10% of the population. So if you're talking about a population of only 1,000 people, you wouldn't be picking 600 people in each sample. The idea is we're trying to keep the sample size 10% of the population size or below, so that when I pick a sample, I don't throw off the proportion from the rest of the population. All right, so let's try to see this in action. Remember that time poll where 42% of registered voters approved of gay and lesbian couples marrying? What if we obtained a simple random sample of 50 voters, n equals 50? What would the sampling distribution of the sample proportion look like? Well, based on our discussion, we should be able to use this information to try to calculate not just the mean of the sampling distribution of the sample proportion, but also the standard error of the sample proportion, or the standard deviation of the sampling distribution of the sample proportion. So we know that n equals 50 is smaller than 10% of the population size. This is something that should be assumed already. The sampling distribution of the sample proportion has this mean, and that should make sense to you because the mean is going to be equal to the population proportion. The standard deviation should be about 0.069. Now, keep in mind that 0.42 is the p value, 1 minus 0.42, that's the 1 minus p, and 50 is the sample size. And that standard deviation is 0.069. I believe that's an 8. I don't know why that was cut off. All right, again, questions that you can answer by yourselves. Now let's talk about probabilities based on sample proportions. We just talked about the fact that if it's a normal curve, doesn't matter where the normal curve is from, we can use normal CDF on it. So in this case, we have 18.8% of school-aged children were overweight. This is a population proportion. In a random sample of 90 school-aged children, here's our n value. What's the probability that at least 19% were overweight? Let's do that one first. Okay, we were able to calculate the mean of the sample proportion very easily, and the standard deviation of the sampling distribution of that sample proportion also fairly easily. For letter A, we just used normal CDF from 0.19 to 10 to the 99th, and that was a straightforward calculation. And then for the second part, 24 out of 90 is 0.267. That's the sample proportion. What's the probability of observing this sample proportion with these values? The normal CDF goes 0.267, which is our observation. The probability of observing a value that large or larger is 0.0276. So that's a very small probability. The probability is only 2.76%. So we call this sample, what might you conclude? We call this sample unusual. All right, this was an explanation of the Chapter 8 data about sampling distributions. Good luck studying.